Hello everybody, how are you today? In this spirit, we will move on to a new lesson of the chapter circles. Subtended angles. At first, we need to know what is the meaning of subtended angles. Let us see. If we are given a line segment, an angle which is facing to this line segment is called an subtended angle. Let us see an example here. So this is a subtended angle, a V shape. So whenever you see the word subtended or subtended angles, you have to consider the V shape facing up or down or left or right. Facing to any side doesn't matter, but facing the given line. Such an angle is called a subtended angle. Let us see a chord for a circle. Let's say PQ is a chord. Then subtended angles are, it can be an angle on the circle to the minor arc, to the major arc, to the center, or to any other interior points or even exterior point on the circle. All these are subtended angles. For example, PSQ is a subtended angle. Angle PRQ is a subtended angle. Angle PTQ is a subtended angle. Angle PMQ is also a subtended angle. So what is the meaning of subtended? An angle which is facing the given line segment. Let's move on with a theorem. Equal chords of a circle. Equal chords. So for example, if this is a circle with given chords, these two are equal. Subtend equal angles at the center. We have to show that the angles are equal. This is what we have to show. It's not given. For that, we know these are all radii, because radii or radius is a line segment joining the center to any point on a circle. So we have a triangle OAB and a triangle OCD. So let us consider the triangle AOB and triangle COD. We can see that AO is equal to OD and BO is equal to OC. They are all radius or radii which are all equal. And we are given that AB is equal to CD, equal chords. It's given to us. So by SSS, these two triangles are congruent. AOB is congruent to triangle, we can say COD or DOC, because both these sides are equal, because they are the radii. So by corresponding parts, we can say AOB, angle AOB is equal to angle COD. So these two angles are equal. That's what we have to prove. Let us see a question now. Prove that equal chords are given equal, in congruent circles. What is the meaning of congruent circles? Circles of same measurement, which means same radii. So we have two circles with say equal radii. Let's say 5 centimeters, 5 centimeter, 5 centimeter, 5 centimeter. And the chords are equal. So let's say this is 7 centimeter, for example only. And this is L, M, N, O. We have two triangles again with two centers P and Q. Now we have to show that the angles subtended at the center are equal. Let us consider the triangle again the same way. In triangle PLM and triangle QNO, we have PL is equal to NQ. Both of them are of same radii. Also, PM is equal to QO, same radii. And we are given that LM is equal to NO, equal chords we are given. So by SSS, triangle PLM is congruent to triangle QNO. By CPCT, we can find that angle LPM is equal to angle NQO. That's what we have to prove, equal angles. Let's see the opposite of the given theorem. If the angles subtended by the chords of a circle at the center are equal, the angles are equal. These two are equal. And this is a circle, so all radii are same. We have to prove that the chord is the same. This is what we have to prove. So once again, let's take the triangle POQ and ROS. In triangle POQ and triangle ROS, we have PO is equal to SO and OQO is equal to RO. All of them are radii. Angle POQ is equal to angle ROS, equal angles at the centers, which is given to us. So we have side, angle, side. By SAS, before we were given equal chords. So we could write SSS, but now equal angle. So we have to use the congruence SAS. Triangle POQ is congruent to triangle ROS. So by CPCT, we have PQ is equal to RS. That's what we have to prove the chords are equal. Let's see a question related to this. Prove that if the chords of congruent circles are congruent means the radii are equal. Have equal angles at the centers, then the chords are equal. So angles are also given equal, then the chords are equal. This is what we have to prove. In the same reason, we can prove that A, B, C, D, O and O dash. So we can say that triangle AOB is congruent to triangle CO-D by SAS congruence rule. Just we proved it now. So by CPCT, we have AB is equal to CD. Which means if the angles at the centers are equal, then the chords are equal. We have to use this theorem in many exercises coming in this chapter. Another theorem, the perpendicular from the center of a circle to a chord bisect the chord. So we are given perpendicular and it is coming from the center. So we have a chord and this line is perpendicular. We are given this is perpendicular. Now we have to show that it bisects the chord. This is to be proved. For that, let us do a construction by joining the radii. O, M, N. So join radii OM and ON. So in triangle, let me mark this as P. MPO and triangle NPO, we have PO is common. Angle MPO is equal to angle NPO is equal to 90 degree because they are perpendicular given. And we have MO is equal to ON, it is the radii. So which condition does apply here? Is it SAS or SSS or some other rule? We have a 90 degree and we have studied a special congruence with 90 degree. 90 degree is called R and the side opposite to 90 degree is the hypotenuse and we have a common side. So by RHS, because SAS does not work here because between the equal sides, we have angle MOP, which is not given. So we can't use SAS. So the only congruence rule is RHS. Triangle MPO is congruent to triangle NPO. Here we have to show that MP is equal to NP. Therefore, MP is equal to NP, corresponding parts of congruent triangle. Hence, the chord is bisected by the perpendicular line. Easy, right? Let's move on to another theorem. The line drawn through the center of a circle bisects the chord is perpendicular to the chord, which is the opposite of it. It's given they are bisected. Now you have to prove that it is 90 degree. This is what you have to prove. For that, again, let us take the construction. So again, join the radius AO and OB. Now in triangle AMO and triangle BMO, we have OM is equal to OB radii. It is the same. We also have AM is equal to MB because M is the midpoint, it is given to us. OM is common. So we have side, second side, and third side. So by SSS, triangle AMO is congruent to triangle BMO. We have to prove that the angle is 90 degree, which means angle AMO is equal to angle BMO at a point on a line. If two lines are equal, we have each line will be equal to 90 degree by linear pair. Because if these two are equal, 90 plus 90 is 180 to form a straight line. So we can see that OM is perpendicular to AB. Let us see one more theorem. There is one and only one circle passing through three given non-collinear points. First, let's recall what was collinear points. Three or more points are called collinear points if we can draw one line passing through all the 3 points. If we have 3 non-collinear points, it is not necessary that we can draw a circle passing through these 3 points. But the theorem says that there is only one and only one circle passing through 3 given non-collinear points. Means we can't have one more circle passing through the given points, let's say A, B, and C. Maximum you can have only one circle. Let's move on to a note here. A circle drawn through 3 vertices of a triangle. A circle which passes or just intersects the 3 vertices of a triangle is called a circumcircle. The name of such a circle is called circumcircle, and the center of such circle is called circumcentre, and the radius is called circumradius. And note that the 3 of its radii will meet the vertices of this triangle because the vertices are on the circle. We may have to apply this rule in some of the examples later on. Let's move on to exercise. Draw different pairs of circles, different pairs, which means you can draw one over the other. No, we have to draw different. How many points does each pair have in common, and what is the maximum common points? Here we have 2 circles. They are not intersected, so we have 0 common points. Here we have just 1 crossing point, so it is 1 common point. Here we have 2 common points. Again, we have 2 common points. Here we have no common points. Again, 1 common point. So maximum you can have 2 common points between 2 circles. Give a construction to find the center of a given circle. We have a circle, but we want to know where is the center. This happens mostly. If you are drawing a circle just with a shape that you have, you will not have a center unless you are drawing it with a compass. For that, what you have to do is just construct any 2 chords. Maybe equal, may not be equal. Let's say P, Q is a chord, M, N is a chord. Next, you have to find the midpoints. Let R and S are the midpoints. So, draw 2 chords, PQ and MN. Next, mark the midpoints R and S respectively. Then we have to apply the theorem that we have studied. The perpendicular line from the midpoint of a chord pass through the center of the circle. So this is a perpendicular. So the center will be anywhere on this line. Again, we will draw one more perpendicular. That's why we made two chords. Again, we have another perpendicular which is from the center. So the point where it meets is called the center, or it will be the center. So we apply the theorem. O is the center because perpendiculars from the midpoint of a chord of chords pass through the center of the circle. This is the theorem that we apply. Moving on to the next question. If two circles intersects at 2 points, two circles intersects at 2 points, prove that their centers lie on the perpendicular bisector of a common chord. So let's take AB is a chord which is common for both these circles. Now we have to show that a line which is passing through the midpoint, let M be the midpoint, and this is bisected, and the perpendicular. Center is on the line, let's call this is O dash. O dash is not a point, it is just a line which is perpendicular bisector of AB. So we have to show that the center is at O or O dash. We have proved by theorem that the perpendicular bisector of a chord pass through the center of a circle. This is the C1 and C2. Center of C1 will be on the line M or dash. Same way, center of circle 2 will be on the line MO. Finally, therefore, centers of these circles will be on the line O dash. That's what we have to prove. That's all for this exercise. See you soon.